Okay, we got exponential and logarithmic functions. So just quick introductions here. Last time we talked about this is so when we have been doing polynomial functions, we have been doing something like this, like 3x squared plus 7x plus 10, whatever, right? Those are polynomial functions. We've primarily been doing those. So now we want to do is we switch something. In fact, we kind of think about this right here. You don't need to write this down probably. If you wanted to write down exponential logarithmic functions chapter 3. Don't write this down. This is kind of just thinking through stuff. So here's what happens here. So technically what we've been dealing with is this is called a power function. You can even write it like this. So y is equal to x squared. Are we good? That's what we've been dealing with. So the next question is this. What happens if I switch my exponent and my variable and I switch it to something that looks like that? And that's the question. It's like things that make you say, I wonder if I do this. And now the question is, what does that look like? What does a graph of that look like? Is the algebra still the same? Can I add, subtract? But hold on, now I'm dealing with exponents as exponents. And then we're going to deal with some other stuff here. So these are guys, they're called transitive functions, which means they're defined way different from algebra. Okay? So another thing, that's one piece to keep in mind, okay? Next thing to keep in mind is this right here. You guys, ever since we started algebra, do you guys remember doing linear functions? Right? Remember solving them and graphing them, right? So then we moved on to quadratic functions, solving them, graphing them, right? Then we move on to polynomial functions, which we just covered here. Anything, quadratic functions are like x squared, and it stays as x squared. Polynomial functions now go to x cubed, x to the fourth, x to the fifth, so it's a higher dimension. And so now we move on to this guy right here. So exponential and logarithmic, we'll define both of those. So that's our next step right there. And then all we got to add to this one would be trig functions. Once you add that, you have pretty much set yourself ready for calculus. That's because that's what algebra is. Algebra is just going through all these different functions until you finish them. You learn how to simplify, solve, and graph. That's it right there. If you guys can think about that, that's all of your algebra skills right there. Simplify, solve, and graph each one of those different types of functions. Okay, let's get started. I'm going to try to get through. Let's see if I made notes here. We're going to get 1 through 4 for sure. If we can squeeze in 1, 3, 5 into this situation, we'll do it. But I do want to get through 1 through 4. So this could be a short chapter, just 4 sections, and we're done. We're good? So if you do have your calculators, you might as well get them out as well, because we'll do some stuff with calculators. So we're going to go with today. Look at this. Today is going to be exponential. Once we finish that, we'll go logarithmic. We'll spend a little bit more time with logarithms because they're a little different sort of fun stuff. And then we'll get to finally equations. So we're getting to solve them. And if we could do a little bit of modeling, real life modeling, that'd be great. But let's jam. So first of all, the definition. So an exponential function has a base of a is our little constant, and is denoted by f of x is equal to a to the x. Few things have to happen. All right, a few things have to happen. The a value has to be a positive integer. It can't be 0 for these guys, but it can't be a negative either. You can't take a negative number to decimal powers. It doesn't work. Might even blow up your calculator. We'll see. Okay. Also, then you can't use 1, because what's 1 to the first power? 1. 1 to the second power? 1 to the third? Fourth? Oh, cool. So if 1 is in there, it's actually a linear function. It's not a exponential function. So we discount that one. But forget 1. We don't do that. Dylan, question. Go ahead. Say again? Oh, yes, please. Yep. Please tell me when you want me to zoom in here. There it is. So exponential function f with base a, and this guy we're going to call the base.
Is that Z is the exponent?
Z is the exponent. X is the exponent.
Wow.
So now x could be any real number whatsoever. We could put in a 2.7, 2.6343. We could put in 3 halves. We can put in a negative 1.364. Anything goes. We could put in a whole number. Absolutely. That's why for these guys, we do need a calculator. Chapter 3 is calculator somewhat heavy here.
Do you want us to start bringing these every day?
Please do. Yeah, that'd be best to do. Okay, are we good? So with the calculator, if you have it available to you, and tell me if you guys are done writing down the definition. So what we want to do is we want to just get familiar with just plugging it into the calculator, see what happens, and then we're going to get onto graphing. And then we're going to look at a special one that occurs in finances, that occurs in nature, that occurs in a lot of other stuff. Exponential function, a certain one. Okay, I see people almost done writing it down, so go for it. Oh, someone's excited. All right.
Yeah, she's here.
That's very possible.
Cool. I think I have it on the next slide, which is big. Yeah, example 1, have it on a bigger slide here. So let's go for it. Use a calculator. We're going to evaluate each of the following. So f of x is 2 to the x. We're going to put in a negative 3.1. Now, real quick here, in your mind, can you do this without a calculator? I don't think so. You're going to take 2 to the negative 3.1 power. Oh, yes. Okay, so. No problem. Actually, let me jump in my calculator. It's a little, we call it a caret. So question is, what do we use? Whoa. That was funny. Sorry guys, 1 second here. Redoing some stuff. Thank you. Okay. That did a lot of funny stuff. Okay, it's not presentation view, okay. All right, calculator right over here. Let's jam with it here. Raise your hand if you have a calculator with you today. Just real quick here. Okay, about half, no problem. So just probably bring your calculator from here on out, especially through chapter 3 here. All right, so let's go with it. 2 is right over here, and this little button right here, it's called the caret button. It's above the divide symbol usually, right there. And if you're just putting in a single number, Charlie, question.
What if I don't have it?
Ah, gotcha. Okay, let me see if I can dig one up somewhere.
You should write on a calculator.
Okay, so another thing on your calculator is this guy's a negative button on your calculator. This guy's a minus button. So those two mean totally different things. So don't get confused between those, okay? So one's a subtract button, and one's a negative button. And if I click on here, I should get a 0.116629. Are we good? Yours says what? Air. Okay, let me check yours. Uh-huh.
That's what I got too.
One of 2 things could go wrong here.
The calculator's the same, please stop.
Right.
It's negative 3.1. That gives you just a second here. Voila, awesome, problem solved. Next one. Now put in 3.1 negative. So we're good. So you're going to have to do a little bit differently. Charlie, good. Bring one. I'll find you. Okay. Bam. Okay. Okay. Try the next one. Go for it. So this one is a 2 to the negative. Negative is actually inside the equation already, but you're going to plug in a pi into it. The pi button is going to be above the caret button, right over here, or your pi button could be somewhere else. You have to find it on your calculator. It just says pi, yeah. So 2 to the power of, and I like to put a parenthesis in there just so I know what I'm putting in. So negative goes in, and pi. And you want to use pi because if you put 3.14, it's going to be off. The digits are going to be off. So you want to use the pi button itself. Okay, and I got 113. Perfect. Okay, so real quick here, are we good there with that one? So 0.1133. Now the question is, how many digits do you put? Let's see if the back of the book tells you, or the calculator exercise equations tell you how many decimals you want to put. 3 decimal place accuracy. That's what.
So we put it on.
0.113. Yeah. The top one would have been 0.117, right? Because you got to round off. Okay, and then real quick here for C, 0.6. 0.6, is that still okay for a number? What are conditions for A? What are our conditions for our base? Base has to be above 0 and not 1. Okay, those are your 2 conditions right here for A. 0.6, does that fit those conditions? Absolutely. Okay, let's punch it in on a calculator. See what we got. So 0.6 to the power of, oh man, a fraction. Here it is. I got 3 divided by 2. Close that off. All right, something close to 0.5-ish. 0.46, looks like 465.
Yeah.
Okay, perfect. Okay, so boom, I'm gonna go here. This is 0.117. B plugged in into this one. Turned out to be 0.113. And C plugged in, just as a reference. Oh, I'm plugging in the 3/2. So plugging in a fraction here. All right, the other way that you could have done the last one there, if you just knew the 1.5, right? That would have been the same thing because 3/2 and 1.5 is the same equivalent, right? Decimal versus fraction. So yes, you could change fractions to decimal as long as it's the same. Okay, are we good there? Jam, and next is, what do the graph of these guys look like? So punch to here. So can you graph 2 to the x and then graph 4 to the x in the same axes here? So let's graph it first of all. Before we do it on calculator, let's graph it manually. And here's how we do it. Whenever we don't know how to graph anything, we always go back to table, because table will get us what we need. We'll go from there. So for A, we're going to make ourselves a little table. Got x and f of x. And then the only thing is with 2, let's see, there are, and see if this makes sense here, there are numbers I can plug in that I can figure out what the values are. They just have to be integers, because I know I can only do integer values. Because I know from algebra 1, I know how to calculate this, I think. 2 to the negative 3. In fact, help me out here. 2 to the negative 3, how do we simplify that? What does the negative inside the exponent mean? What do we do with the 2 if we have a negative in the exponent? Yeah, pretty close. Yeah, pretty close to it. So make it a fraction. You could either take a 1/2 here, or you can go like this. You could take it's called reciprocal. A negative in the exponent means reciprocal. If it was on the bottom, if it was 1/2 to the -3, then what we do is we bring it up to the top. So in this case, 2 times 2 times 2 is 1/8. Are we good? Okay, 2 to the -2 power is going to give us 1/2 squared, which is 1/4 this time. Oh, okay, these are small fractions on this guy. Okay, so 2 to the -1, that just means we're going to just take, oh, that's cool. That's just 1/2, right? 2 to the -1 means reciprocal of 2, which just means 1/2. Ah, anybody, 2 to the 0 power. 1, yes, any number to the 0 power is 1. 2 to the 1 is a 2. 2 to the second is 4, and 2 to the third is a 8. And notice the little pattern that we have here, right? The difference between the +3 and the -3 is a reciprocal difference of 8 and -8.
Are the graphs never constant x-axis?
Oh, perfect. Yes. So if I were to graph, we're gonna graph it on a calculator here in just a bit here, but we should note a little something here. Hey, Abe says it never touches the x-axis. Doesn't that mean it's something called a horizontal asymptote? Love it. So yes, right there, there's a horizontal asymptote these guys have. Yes, as long as it's not moved, as long as it's like 2 to the x, 3 to the x, 4 to the x, 5 to the x. Cool. The other thing that we note is this little piece, this is going to be an important number for us because any number to the 0 power is 1, right? So that guy is going to be there quite a bit right there. Right. And then the other one that we do is math, like, oh, that's an easy one to graph, is this one right here. Because if you take that number to the 1 power, you're just going to get that same number back, aren't you? So in this case, 1, 2 is what we have here. So let's just do this a quick graph. This little quick graph, if we're to graph it, that's -1, that's -2, that's -3. So at -1, it's a 1/2. That means it's a 1/4. Now we got ourselves a 1/8. So that's what these graphs look like. Okay, so it looks like I'm gonna change my pin color even. I like purple today. So it goes like this. It's almost like a flattened little piece, very close to 0, and then all of a sudden it starts going, and then at, oh, this is up to 4 already here. 4, and then I'm not even gonna do 8. I'm gonna just show the fact that it's going up fast. Oh, don't forget 2 arrows at the end, right? Arrows on this side, because it goes both ways. Boom. All right, you guys talk to me. Does that look like anything that you would, anything in real life that does that? Like flat for a while and all of a sudden it goes up quite a bit. Dylan?
Sounds like the COVID charts.
The COVID charts, yes. We got a spike in things. Okay. Anytime you get sick, you have a virus or a bacteria, like a bacteria infection, you don't have it at all, right? And then you get it, and then incubation period for bacteria is about 3 days-ish, 3 or 4 days. So if you get exposed to bacteria and you actually are developing a sickness, you won't see it for about 3 days, then you get sick, right? That's it right here, because then you get to go to bed with some nice cup of tea and you sleep. But that's it right there. It's and then eventually it's right, it goes down again, then you're over. If you go the other way, we'll go the other way a little bit later, but if you go this way, I'm thinking like the value of cars, right? It goes down quick. Yeah, it's go down super fast, and then at least goes down slowly. This one also in chemistry or in archaeology, we call this a decay curve or radioactive decay measurements. They go down like that. We also measure, we measure population growth like this as well. Population growth would measure like this, whether of humans or of prey and predator species.
Yeah, but doesn't population limit?
Yeah, and then it'll cycle back around. Usually exponential functions are made for like a certain period of time. So from here to here, that's how much you have. So that's, and then interest on money. Putting away a certain amount of money for a little while, as long as you get a certain percentage, eventually gets you.
Oh, global warming. About time.
Cool.
1945, everything went up.
I wonder why. Anyways, we're good there. So yes, application to life, at least somewhat there. Okay, let's go with, I think we can graph this on, let's graph 4 to the x. Let's graph the b part on here. And let's see how they compare, f and f of x. So -3 are usually plug-in values, -2, -1, 0, 1, 2, and 3. And let's see how that compares to this one. Let's see how much time we have. We at least want to get things here. All right, so I have 4 to the -3, which makes 1 over 4 to the 3. And what is 4 times 4 times 4? 64, perfect, 1/64. Okay, 4 to the -2 becomes 1 over 4 squared, which is 1 over 16.
Can you divide by 4? If on the last one, you could divide by 2.
Absolutely, yep. 4 to the 0 power, again, is 1. 4 to the 1 power, 4. And you know what, we can even do this. How about 16, 64?
I just did 4 to the 4th, and it just goes to 256, so it's not that high.
So with
Yeah.
these, once you get one side, it just mirrors the denominator on the top, right?
Mirrors the denominator? Yes, correct. So let's do this one. Notice, I want you guys to notice a couple of things here though. As you graph -3 1/64, notice the graph is going to be slightly under. It's going to be like right here, the dot. 1/16 is going to be right here. 1/4 is going to be right here. We're good? So notice the graph is underneath the other graph. Then at 0, 1, hey, that important point. Remember that little guy important point right there? 0, 1 again. And then at 1, that's going to be 1, 4. Oh, that's interesting. Look at that. So it was underneath the purple line up until this little break. And then after, I'm not even going to graph this one, up to 16. Forget that one. So it looks like this black line for x to the 4th is going to be underneath the purple line. And then it crosses right here. And then from here on out, it's above. Interesting, okay. So we say it sticks down to 0. If you go to the left, those guys go to 0 a lot faster. Okay, jamming, that's cool there. Are we good with that? We're good with 2? Moving on to 3, let's switch it around. What happens if? What happens if I put a little negative in the exponent? What's happening with my graphs? And so let's do a table for A, and I think we can do B real quick here, even without a table. But let's just do the table for A. So now this is f of x equal to 2 to the -x. So let's see what happens here. If I plug in a negative of a -3. Yeah, that little negative, what it did is it switched my x's and y's around, right? negative 2 positive. So this just becomes 8. Oh, that's 3. Cool. So 2 to the negative 2 with 2 to the negative of a negative 2 becomes 2 squared, which is 4. Can we fill in the rest of the list here? 8 down to 4, down to what? 2? Down to a 1. What's going to happen after that? 1. Perfect. Okay, so what does this graph look like now? Let's graph this guy here. So 1, 2, 3, 1, 2, 3, 2, 3, 4, 2, 3, 4. So negative 3 now jumps to 8. I'm not going to graph that one. Negative 2 graphs at 4. Okay. Negative 1 graphs at 2. That's cool. Hey, there's my 0, 1 again. This seems to be a very interesting point. Then I have 1, 1/2, 1/4, 1/8. Oh, that's so cool. So I have something that looks like this. Boom. What am I missing in my graph? I'm missing something. I'm missing something. Say again, Charlie? Arrows, yeah, got the arrows. Boom. And it's not gonna show as well on the graphs you have in your textbook either, but we have, thank you, horizontal asymptotes right here. Except whenever it's on the y-axis, your book does not show the horizontal asymptotes, but you have to understand they're still there. Good. I would prefer you guys graph them in. Okay, talk to me. Can we graph, it's not gonna be precise, but can we graph 4 to the negative x based upon this stuff right here? I think we can. Let's see. It's going to go up faster, right? So it's going to come down like this faster. It's going to hit 0, 1, but then underneath, it's going to go underneath the red line and kind of hugs the y = 0 line a lot faster. Okay, are we jamming? So there's your radioactive decay. There's your value of cars right over here. There's your beginning value. Car is worth $60,000 to start with. So the $60,000 will be along the x-axis, and then all of a sudden it goes down like this.
Never reaches 0.
Never reaches 0. Even if it's a clunker, someone will be willing to pay at least scrap metal for it. Okay, jamming, we got that one. Next is in your book, you do have these guys. So I just want to show them to you here. This is a to the x. It goes through 0, 1. So let's talk about this. Oh, let me move this little guy around here. Just go away somewhere. Okay, graph of a to the x if a is greater than 0. Or greater than 1, sorry, it's greater than 1. So notice real quick, domain. Domain, we can graph anything we like, right? We can plug in any x value. Range is going to be anything higher than 0. The y-intercept is 0, 1. There's no x-intercept. This guy's always increasing. There's a horizontal asymptote, and this guy's continuous. This one goes the other way. Still domain is the same, range is the same, intercept's the same, except it's decreasing now all the time. And we still have a horizontal asymptote. Okay, are we good there? Okay, one other thing. It's this little part right here. If something is increasing all the time, or if something is decreasing all the time. Hey, Camille. If something is increasing all the time or decreasing all the time, we say that this guy is something called 1 to 1. Just something in mathematics. Paula, the stuff that we graphed in the last chapter, these guys are not 1 to 1. Remember these guys from last chapter? Notice the y values start repeating themselves. So here's good, Here's good, here's good, here's good. Then when you go down here, I got repeating y values. One-to-one functions are important to us because we'll do next is we can find something called inverses of them. Good. Okay, we good? You probably don't need to write all this stuff down. It is inside your textbook here. It's on page 220. If you want to refer back to it, you might as well just sort of have it. Just pay it right to page 220 there. It's cool. Okay, we're gonna do a lot more. We're gonna do a lot more graphing of this stuff in just a bit here. But let's go real quick here to solving equations here first. So let's jump to this one here. So example 4 says, notice that this is a one-to-one property. That's okay, but can you solve these equations? In algebra 2, yeah, in algebra 1, did you guys solve these guys or no? With exponents? No, okay. So this is a quick, okay, that's cool. Let's go slowly on this one here. So what allows us to solve these guys is you can get the bases to look exactly the same. So a base of, or a 9 and a 3, can we get those guys to have the same base? I don't know. What do you say? Too easy.
I mean, I can't really read it, but I'm assuming it's 3 to the x, is that x plus 1?
3 to the x plus 1 on one side, yeah, and there's 9 on the other.
Well, if we put in 2 to the x, or sorry, 1 to the x becomes 3 squared.
Oh, perfect. Okay. Owen says I could just guess this. So that's right. It says if I put a 1 in here, that makes 2. That makes 9 to be a 4. Perfect. I was thinking going the other way, going like this right here. So 9, I'm going to make these bases to be exactly the same. So 9 is really 3 squared. So if I can make these bases to be the same, notice it's going to be 3 to the second power and 3 to the x plus 1. We good? Once the bases are the same, what I'm allowed to do in math is drop my bases, because those are the same now, and I'm only going to work with the exponents. So 2 is equal to x plus 1. And I start solving. Again, these are really easy anyways. So I know how to solve this in algebra. I subtract 1 from both sides. I get 2 minus 1 is 1, and x is equal to 1. Are we good there? And like Owen said, that's easy, because I know that's to be true, because 1 plus 1 is 3 squared, and 3 squared is 9. That's easy. Okay, so name of the game here is make these bases to be exactly the same. And can we? So 1/2 and 8. That's so weird. Okay, how about this, guys? How about 1/2? Isn't 1/2 a reciprocal of 2? Is that right? So talk to me, see if this makes sense. 1/2, I'm going to do this. I'm going to make that into a 2. I'm going to have to make this guy into a negative there. Is 8. Can I make 8 into a base of 2? Yeah, 8 is 2 to the third power. Yep. Do I have my bases to be the same? Absolutely. I can forget the bases and just solve for the exponents. And I get x is equal to -3. And let's see if it works. Let's see, I'm going to plug it back in. So 1/2 to the -3. Question is, will that give me an 8? Yeah, we take the reciprocal of 1/2, which is 2. And 2 times 2 times 2 is 8, and it checks out. Huh, okay, it's interesting. Yeah. Let me check something. Let's see if we can do. Okay, we should do this one as well here. So let's graph one more before we quit for the day. I'm going to say this is example number 5. I'll change it up later here. Example number 5, graph. That one, and then we've got one more about that. So 3 to the x minus 2. Now here's where the fun begins. So I have something else in the exponent now. We still have to do this. The only question that we have is, what's my middle little point going to be? What causes a 0 in the exponent if I'm subtracting 2 from it? Yeah, notice the 2 should be in the middle, right over here. That's 2 because that causes the 0. So I'm going to go 1, 0 this way, and I'm going to go 3, 4 that way. So slightly different now. And here's the one that I'm targeting because I know that 3 to the 2 minus 2, give me 3 to the 0, and that's the one that causes the 1 for me to happen. And usually we want to at least get back to the 0. That's what we want to do because we want to see what the y-intercept is. So 3 to the 1 minus 2 makes 3 to the negative 1, makes 1/3. Three to the 0 minus 2 makes 3 to the negative 2, or 1/9. Everybody agreed there? All right, can you go the other way now? 1/9, 1/3, 1. Boom. What do you say? 3 and 9, is that right? I'll even do the work here though. 3 to the 3 minus 2 is 3 to the 1, which is 3. 3 to the 4 minus 2, which is 3 squared, which is 9. Okay, the graph of this guy. So 1, 2, 3, 4 out. And 1, 2, 3 up, or maybe 4 up, and that I don't need to go any more than that. I'll make my graph 4 everywhere. So 0, 1/9 is going to be this little dot right there. 1, 1/3 is going to be here. 2, 1, that's my little important part right there. 3, 3. And that's it. So hold on real quick here. How come it doesn't go through 0, 1 anymore? Yeah, I got a little extra piece in the exponent now, right? Remember the graph that we had before? These guys right here, this is the basic one. Basic one is just y is equal to a to the x. There's nothing added to the exponent. There's nothing new in the exponent. It's just the basic one. So now I subtracted 2 into the x when I have this. Boom, what am I missing? What am I missing? The horizontal asymptotes. I like drawing them in. Okay, one more. Everybody good with A? Cool. Let's jump to B. Oh, not that yet. We'll do that next time. We got one more. Come on, scoot out of the way. And part B, f of x is equal to 4x minus 3. Oh yeah, plus 3. There we go. Actually, let me put a plus 4 on here. Oh, sorry. So it'd be x plus 3, just to give you guys a plus in the exponent now. Oh yeah, this is interesting. Now I have this extra little +3 in the back end over here. Sorry guys, can we change it up just a little bit, just so the numbers are not all the same? I'm gonna just put a 2 here, just so we don't have a 3 and a 3. Hate when math teachers or math problems, they have the same number in both of them and they can't tell which one's doing what. Okay, what's my middle number now? Tell me if you guys agree, -3 is my middle number? Yeah, and the one that I'm looking for is that little guy that gives me that little 0.
So it doesn't matter.
It's almost like that little point before it starts really going up. You know, that little curve there. So 0 power is 1. 1 plus 2 is a 3. Perfect. So I'm going to go -2, -1. I'm going to go, oh, sorry, the other way. -4, -5. This way is going to be -1, -2, -1. Okay. Let's punch those in real quickly here so we can finish on time. So I plug in a -4 plus 3 makes 1/4 plus 2, so 2 1/4.
Would you want to keep it as an improper fraction or
Mixed number, yeah, because then I can tell where the line is, where I need. This one's going to be, let's see, 4, -5 plus 3. Let me do it in pieces here. This would be -2. This would be 1/16 plus 2 more. So 2 and 1/16. Ooh, a little different than we started off with today, huh? Slightly different here. 4 to the -2 plus 3 makes a 4, and then add 2 to it makes a 6. 4 to the -2 plus 3, or -1, sorry, -1, makes 4 squared, which is 16 plus 2. You guys check my math here. Is that true? Is that all making sense there? 16. I said 18. I said, yeah, wrote down 16. Okay.
you can still kind of use the denominator. Take the denominator, add the whole at the end.
Correct. Yeah. So there's some patterns here that emerge. Okay. Let's see if we can graph this guy. So maybe I'm going to move this guy over just like this right here. It won't be a perfect 1, 2, 3, 4, 5 backwards. And 1, 2, 3, 4, 5. I think I'm going to go up to 6, just so I can capture that little -2 there. Okay, so let's go with -5. It's going to be a 2 and just a little bit higher than 2. At -4, it's going to be a 2, just a little bit higher than the previous one. At -3, it's going to be actually right at 3. At -2, it's going to be all the way up at 6. And at -1, forget it. So let's go with it here. Here's my dots. Here's my curve going through the dots. Can't say a line because a line by definition is already straight. Boom, here's what I got. What am I missing? Thank you. Where is my horizontal asymptote? X equals 2. I agree with Isabel. That little guy right here shifted my graph up 2 units. And because of that, I should have a horizontal asymptote that's coming down right. Yeah, these guys do not have vertical asymptotes. They're only horizontal asymptotes. Now, logarithmic equations, those guys will have vertical asymptotes. So we'll get to those. Okay, guys, done for today. How about that? You learned about this stuff. Not ready to do the homework just yet, so we'll spend on Wednesday finishing it up, and then they'll assign the homework. All right, and have a great day. Thanks.
Thank you.